hydrodynamics works very well on the scale of 1 to 10 Fermi scale. That's basically in the nuclear scale on the size of a proton or large nucleus. So on that scale, relativity hydrodynamics works very well in this kind of collision. The hot matter is created in the collision, and that expand hydrodynamically. So without going into further detail, let me say this is what we found from the last 20 years. And then in the last 10 years, the field starts to move into a different direction. Not only that we want to make material that are extremely hot with very, very high temperature, we also want to look at materials with extremely high baryon density. So that was the start of the beam-energy scan program, especially at the Relativity Hadron Collider at RHIC. The idea is that they kind of also mentioned in the last seminar that we have one important control of the Hadron collision, and that is the beam energy. By systematically turning down that beam energy from like 200 GeV down to the order of 10 GeV or even lower, you can actually access different parts of the so-called QCD phase diagram. Starting from the very hot region, you gradually go into a region where the baryon density becomes larger and larger and larger. Of course, the main motivation for that physics program is to look for the true kind of phase transition, like a critical point or first order phase transition between quark-gluon matter and hadronic matter. It turns out that we got a really wonderful bonus from that program, and that's the discovery of the most vortical fluid. That was really kind of something that was not totally expected. As I said, the main purpose was to look for those phase boundaries shown in this plot. But it turns out that by doing this kind of beam-energy scan, you actually can access a region where the material is really rotating or swirling very, very fast. So that has been named as the most vertical fluid. This I often use the analogy with the discovery of the American continent by Columbus. So Columbus kind of had the idea that he started out from Spain. He basically tried to convince people. Of course, he convinced himself that if you keep going toward the west direction, you eventually should end up at the India. That was his hope. He wanted to look for India. That idea, of course, was correct because Earth is like a sphere, like a round, right? But before he was able to actually reach the true India, he of course ended up in the American continent. That's how he discovered the American continent. This is like kind of similar. So before we're still of course working very hard to look for those phase boundary like a critical point of first order transition. But even before we get there, we actually find something quite interesting, and that's what I'm going to tell you today. And let me also say that this really introduced a new handle for us to study the quantum Chromo matter. We used to say that there are extreme conditions like hot temperature or high baryon density where you can try to see how the QCD system evolved under those extreme conditions. Now we have one more handle, and that's fluid rotation or global rotation. That really opened many new questions. And if you think about it, in this picture, I was telling you that in the past 20 years, we were able to figure out that the material will undergo relativity hydrodynamic expansion. That conclusion largely based on the study of the energy and the momentum transport in the quark-gluon plasma that you create in the collision. For a long time, we ignored basically the spin degree of freedom. It's only that in the last 5 or so years that we started to really try to understand what happened to spin degree of freedom in this fluid. And that because we now have a new external control on strong interaction matter, and that's the angular momentum. The angular momentum transport in this material is really a question that has just started to be explored. And I think we also have the very nice experimental access to those kind of angular momentum transport by measuring the spin polarization in inner global or local spin polarization. Okay, that's the kind of general background. And recently, together with many colleagues, we actually published a book with the Springer, and that's the strongly interacting matter and rotation. This is the book that I edited together with Francesco Beccatilli and Mike Lisa. It included 12 chapters, and I think essentially that cover pretty much the relatively recent development in this direction. Okay, many of those chapters are actually available in the archive. And later I will also mention some of the relevant chapters in different parts of this this talk. And then we thank many of the colleagues who contribute to this volume, especially some of you are here, like Xu Guang, like Professor Liang, and other colleagues here. Okay, so this really, so what's the physics of rotating matter? We particularly are interested in something that we call rotational polarization. This is really a long story. It went all the way back to 100 years ago. There was a gentleman, Barnett, who was at the Ohio State University at the time. So he was very much intrigued by a famous effect that's called Einstein-Haas effect, which basically says that if you have a magnetic material and you change the magnetization of that material, you can call it mechanical rotation. He was intrigued by that, and he actually came up with the idea that the reverse of the Einstein-Haas effect could also happen. So this, as you can see, is like really early 1909, and then later on 15. He proposed that if you have a solid material like this cylinder, which is a magnetic material with magnetization, and you start to rotate that sample, meaning that you change the angular momentum of that sample, you will actually be able to detect the change of the magnetization of the material. Okay, so that's basically the reverse effect of the Einstein-Haas effect, which is known as the Barnett effect. Not only that he pointed this out, he actually tried to measure this effect. He measured precisely both the Einstein-Haas effect and Barnett effect. In fact, he was the first to correctly measure the Einstein-Haas effect. So he was able to help us figure out actually that this kind of magnetization really is due to spin rather than the kind of orbital motion of the electron. Okay, that's a long story, but let me cut it short. The essential physics assumption underlying this Barnett effect, namely when you change the angular momentum or rotation of that sample, your magnetization will also change. The essential physics behind it is basically the rotational polarization. What that means is that if you have your macroscopic rotation of your sample, solid sample, which means the global angular momentum, that will polarize your microscopic spin of your particles in the sample, basically electron in this case. Your electron will start to, or your nuclear spin in the material, depending on the specific material. Basically, the microscopic particle spin will be more aligned with your global angular momentum than anti-aligned. Okay, so this is essentially what happened in that case. But even though that was understood 100 years ago, it's actually tricky to see this effect in a real fluid, instead of a solid sample. And also, of course, it's less obvious in the context of a relativistic system like the QCD system that we're interested in. Let me also mention that in other systems, like for astrophysical system, there could be also important role by rotation, like in the neutron star, which are typically rotating. So to understand why there's this effect, namely why there's a kind of rotational polarization, you can take a look at the Dirac-Lagrangian rotating frame. So imagine that you have a system of Dirac fermion, which is spin 1/2 fermion, and you put them under slow rotation. Okay. In that case, you can go to the rotating frame, which is a non-inertial frame. In that case, in a relativistic non-inertial frame, essentially you're going to see gravity. According to Einstein, there's no difference really that between acceleration and gravity. So if you're a rotating frame, you have the acceleration, and you will feel some change of your space-time. Okay, and that can be incorporated into the Dirac-Lagrangian in a proper way. And if you go to the slow rotation limit and expand everything in the linear order of your rotation vorticity or angular vorticity omega, you'll get the Dirac-Lagrangian like this. You can also turn that into a Hamiltonian. What you can see that, in addition to your free Hamiltonian, you get an additional term that takes the form of omega dot j. J is the total angular momentum of your particle, both the spin part and the orbital part. So this is essentially a rotational polarization effect. It says that when you are having a real rotation, your particles will feel that global rotation, and its energy lower when the angular momentum is aligned with the angular speed, and its energy will be higher when it's anti-aligned. Okay, so you can solve this, free particle state under this Hamiltonian. In this case, of course, you can see that the system is no longer isotropic. You have a rotating axis around Z, and you have these good quantum numbers. Let me skip all technical details. Basically, you can figure out what you would call the U and V, the Dirac spinor in this rotating case. And you look at the energy eigenvalues of that Hamiltonian, you will see that these are the usual kinetic energy. You have Z direction momentum, transverse momentum, which is on the plane perpendicular to your angular momentum direction, which is the Z direction, and the mass. So this is the usual kinetic energy, but on top of that, you got this rotational polarization. N is the angular momentum along the Z direction. Is a quantum number for that. 1/2 comes obvious from the spin. So again, you can see that there is a rotational polarization energy associated with individual particle state. And if you actually have a thermal system of those particles, meaning you're thinking about a rotating system which at finite temperature is then obvious to see that because of the Boltzmann factor. For a moment, let's forget about the Fermi or Dirac, Dirac or Bose-Einstein. Crudely speaking, you will get this thermal factor, meaning that your particle will spin up, will have a bigger chance due to the thermal distribution. So under this rotation or angular vorticity, you have more particles with spin pointing up than pointing down. So that leads to a rotational polarization on a macroscopic thermodynamic scale. Okay, so I hope that explains a little bit of what's going on here. And that actually, I should say that to really allow this to happen, you really have to have some, microscopic interaction process like scattering that actually allow the orbital and spin coupling. Otherwise, they are going to be decoupled first. So that's also important. Let me also mention that there are a lot of interest from other fields of physics that are studying this kind of rotational polarization. Like in the condensed matter physics, in particular for fluid. Okay, so you can see these are two recent studies, one published in Nature Physics, the other published in Nature Communication. What they are trying to do is that they're trying to run some like liquid like the mercury, in a certain particular setup, so that you can have some vorticity generated in the fluid, and the hope that those kind of vorticity will control the spin of the electrons that are flowing together in the fluid. Okay, so the essential idea is like this: you are trying to generate some vorticity to control the spin polarization. That's offers some general motivation for us. It's an interesting phenomenon that's still being studied also in the condensed matter. In our context, we have a very different kind of matter, and that is the quantum Chromo matter. It could be a quark gluon plasma, or it could be a hadronic matter. In either case, it's a hot relativistic, quantum Chromo matter. We want to understand that system under rotation. Okay, the plan for the rest of the talk is that I'm going to cover those three different aspects of this direction. I will discuss mostly the phenomenology of rotational polarization in heavy-ion collision. Okay, especially the global polarization of hyperon. Then I will discuss a little bit about the theoretical understanding of angular momentum in hydrodynamic framework. In the last part, I will briefly discuss some nontrivial effects of rotational polarization on the phase structure of matter. Okay, so the first part, rotational polarization in heavy-ion collision. These are some of the relevant chapters that really from the book that cover this topic. So if you're interested in some of the details, I would suggest that you consult some of those chapters where a lot of details are available. So let me start with the first important quantity, that is the angular momentum. So for whatever that I'm going to tell you, that's the starting point. Namely, the collision system has a huge angular momentum along with all the energy that is available. That's something that was often ignored. Actually, I think it's fair to say that it was Professor Zhuotang Liang and Xinliang Wang who first emphasized the angular momentum around 2005. In that very nice paper in 2005, they pointed out that the system carries a non-zero angular momentum, and that angular momentum through the spin orbital coupling can turn into spin polarization of the particles that are produced from such collision. Okay, indeed, if you look at this system, so this is the beam direction. These are our two highly Lorentz contracted nuclei that are colliding. If they're in a non-central collision with the mismatch in the center of each nucleus to be about b along the x direction, then it's very straightforward to calculate the total angular momentum of this system, in a classical way. So that's the number, basically the R cross P, right? So this is the number. A is the nuclear number, B impact parameter, root S is the beam energy. If you put in number for something like RHIC, top RHIC energy, you get something like 10 to the 4 to 5 H bar. This is a huge number. We know, of course, this system is only on the size of a typical nucleus, right? It's like 10 Fermi across. For some of the large nucleus with like high spin state, you perhaps can get something like to several 10 or up to 100 H bar of angular momentum. But for our colliding system with about the same spatial volume, you have a much larger angular momentum carried by the system. Okay, so what will that angular momentum do? Of course, as I said, they already pointed out, through the spin orbital coupling, that can turn into the spin polarization. A somewhat more more fluid dynamical formulation of what happened was proposed by later by the Beccatelli and a few others. Namely, it was argued that this angular momentum will turn into fluid vorticity, and that fluid vorticity in a thermodynamic equilibrium will generate spin polarization for the particle. This is, of course, basically the rotational polarization that I just mentioned in the introduction. Okay, so this is the kind of master formula in that fluid dynamical scenario. Your thermal vorticity, this basically quantifies the rotation in the fluid through the particle distribution, and a freeze out will turn into a non-zero spin polarization of the particle. Okay, so I kind of got interested in this problem around 2014, 2015, and a part of my motivation was really about possible chirovertical effect. I wanted to kind of figure out how much vorticity we can get. So that's when we started doing this kind of calculation, trying to figure out how that angular momentum turn into vorticity. Okay, so that was this paper. There were a few non-trivial questions. For example, when we have this kind of rotation, of course, not all of this angular momentum is actually retained in the fireball, because a lot of spectators will take away a big fraction of that momentum. Indeed, our calculation finds that only actually perhaps about 20% of that angular momentum stay in the fireball. Okay, actually that strong depends on collision energy. At high energy, that fraction is even lower, and low energy, that fraction is higher. But we also noticed that whatever fraction that's been put in that fireball is actually conserved in time. So that's good. So that means your angular momentum is not going away. So that's good news, because then you have to accommodate that angular momentum, because angular momentum is conserved. And then the question is how the QGP or whatever hot matter that you create would accommodate this angular momentum. And the answer is that it will develop fluid vorticity. So these are some of the results that we got from the paper, like the centrality dependent, and in particular the beam energy dependent. You can see that with either a simple hard sphere model for the collision or a simulation like the transport simulation, you will see that angular momentum along the out of plane direction grows almost linear with beam energy. So it's a very strong increase when you go from low energy to high energy collision. That then brings us to a kind of surprising finding from that paper. At the beginning, we were very surprised. So this on the plot on the left shows you the kind of complex vorticity structure that you have in the fluid. You may wonder why this is so complicated. Well, that's because our QGP fluid is really a very highly compressible fluid. It's not like a rigid body. If you have a rigid body, you have angular momentum. It just rotates like the whole object. But the fluid, especially a relatively soft fluid, it won't do that. When you have angular momentum, you will start develop a lot of local vorticity structure like this. Okay, but if you average over the whole fluid in a proper way, well, that's of course actually a tricky question. We spent quite some effort in this paper to discuss how to do an average of vorticity. But in any case, if you calculate define and calculate average of vorticity, those plus minus showing in this structure will not cancel out. It has a non-zero finite average of vorticity, and that's because you have a non-zero angular momentum, global angular momentum. Okay, so we plot this average of vorticity as a function of time or at different beam energies. So here's the surprise. It turns out that this average of vorticity becomes larger and larger and larger when you go from high energy to low energy. This is exactly opposite of this trend. So that's why I say at the beginning it was kind of very surprising. But later on, we kind of understand there are several reasons. First of all, when you go from high energy to no energy, the amount or fraction of angular momentum that you keep in the fireball become higher. And also, when you go to high energy from no energy, you're stretching in the rapidity, okay? So the angular momentum is less spread out in terms of rapidity. So in the mid rapidity, you have more angular momentum. And finally, in the no energy, you create a fireball with less mass and energy. In our classical mechanical language, that means you have a less moment of inertia. So even with the same angular momentum, you will have a higher angular velocity. Okay, so there are several factors that contribute to this behavior. But in any case, the key, I think, finding was that the vorticity basically at order 10 GeV collision is much larger than the vorticity at 100 GeV collision. That turned out to be quite important for later discovery by the Star collaboration, who published a paper in Nature, the cover story in 2017. And this is really an exciting discovery. Namely, by measuring the global hyperon polarization, they were able to say that our core gluon matter or whatever hot matter created in this heavy-ion collision is not only the hottest matter, not only the most perfect fluid, it's actually also the most vortical fluid. So this is the experimental measurement. They measure the so-called hyperon, spin alignment or polarization with respect to the global angular momentum by using very nice analysis technique. So that's the signal they found, the function of beam energy. You can see that, as I said, this really kind of bonus of the beam energy scan program. They took a lot of data starting from 2008 for the beam energy scan program, but that data can be used to analyze this global hyperon polarization. The signal turned out to be strongly increasing toward no beam energy. You can see very clearly this trend. You can extract an average of vorticity for explaining this signal, and that's obviously perhaps the most vortical fluid. That vorticity that you extract on your 10 to 21 to 22 per second is much larger than any other fluid that we know that can rotate. Okay. On the right, you can see, of course, this is the experimental signal, and natural question is whether one can understand or compute that signal from theoretical modeling. You can already see that this trend is kind of consistent with what I just said about the vorticity trend. Okay, so it's natural to say that maybe that's just reflecting the increase of the vorticity. That's more or less the case. You can see for all these different models, calculations based on parton cascade, hadron cascade, or hydrodynamic, pyrokinetic theory, free fluid, they all describe those data and especially the energy trend very well. Okay, it's like out of the box without much fine tuning. Pretty much everybody were able to describe that. So that's good news. That means there's some robust phenomenon that's going on. And it seems that the kind of scenario that you have an angular momentum which turn into fluid vorticity, which turned into particle polarization, is a correct and robust interpretation of this data. Okay. But of course, there are many questions that are not solved. Actually, this was really the start. It's like 2017, and after that is about roughly in the past 5 years, a whole lot of new measurements were made, and a whole lot of new theoretical studies were performed. And actually, there are several interesting directions that are still under intensive study. For example, experimentalists measured different kinds of local polarization patterns, like the polarization not along the y direction, but along the z direction, like the beam direction. They also look at the polarization along the y direction, but they look at the mutual angle distribution. Like when you go around the angle here, how does those polarization change with your mutual angle? It turns out that there are some interesting puzzles, like your local polarization pattern have somehow opposite angular dependence, compared with the theory. Those theories, as I said, they all can describe this global polarization fairly well. So apparently something is missing. And recently there have been some new ideas, for example, from Yin and Hui Tao, and also from Francesco Beccattini and collaborators, namely the so-called thermal shear may contribute to this local polarization pattern. It's like essentially kind of an out of equilibrium contribution. Okay. There are also very nice measurements about the vector meson alignment. So if you think about this, vector meson like a K0 or like the phi meson, they have spin 1, or the hyperon has spin 1/2. So they should feel somehow more strongly the polarization effect. Indeed, that should be the case if your fluid vorticity and rotational polarization picture would be correct. The alignment measurement turned out to be very challenging. I mean, and especially it's hard to interpret. I don't think at this point there's a very satisfactory understanding of what's going on with the vector meson alignment. There are many people working on this. For example, the group of Jin-Feng and collaborators from USTC, they have some ideas about possible source of this, but I don't think this has been resolved. Okay, so this is certainly quite puzzling. Both the measurement at RHIC and also at RHIC by Alice turn out to be, I think, quite interesting and strange. Okay. Another question is that what happens when you go really down to energy like a few GeV collision. So if in this data you can see that there's a trend of going up, down to 7.7 GeV. And natural question, what's going to happen below that? Like when you go down to 3 GeV, let's say, is it going to continue shooting up, or is it going to turn back and drop down? That's a question mark. At least that was a question mark before the 2021 data. So that's an interesting question. And that concerns the question that I put here. Where is the most vertical phenomenon? Meaning that where is the maximum of that spin polarization phenomenon? There are also possibly a splitting between the polarization signal of the particle and antiparticle. If you look very closely into those data here by star, the red circles are for anti-hyperon, anti-lambda. The stars are for lambda. You can see there is a visible difference, even though the statistics is not strong enough to be conclusive, but you can see visibly the difference. So you have more polarization for antiparticle than particle. The question is why? Okay, so this is also, I think, a very interesting question to be understood in the next couple of years. We have some ideas, but not conclusive. I'm going to discuss the last two topics here. So let me first discuss the trend of that global polarization toward order 1 GeV collision. This is really an interesting question. I was much intrigued. So I was told that STAR was taking the fixed target collision data at like 3 GeV and 5 GeV. So that sounds like interesting. If one can figure out what's going on in that region. So that's why we wrote this paper last year. We basically extended our previous calculation at relative higher energy all the way down to a few GeV. Okay, so you can see we systematically mapped out that global hyperon polarization signal as a function of beam energy for several centralities. You can see, up, at 7.7 GeV and up, we can describe pretty well the experimental data. And what we saw in our simulation is the turning down like this, like when you are below 7 GeV or so. Okay, we saw, of course, many other results like differential dependence, no polarization in the paper, but the main result was this. And why, you may wonder why this start to turn back down. Okay, so first, one needs to understand, at least from the simulation, what happened in this region. There are two factors that contribute to this behavior. The first is that the vorticity itself started to turn back. And that's understandable because actually when you go down in beam energy, you will get less and less angular momentum. No matter how much fraction of that angular momentum stays in the fireball, your overall angular momentum is continuously decreasing. So you would expect that eventually that vorticity should turn back down. Okay, so that's what we saw indeed from the simulation. And the other contributing factor is the energy of the hyperon. You can see this is the formula that I mentioned earlier from Francesco. This is essentially the thermal production model for spin degrees of freedom. Okay, it turns the vorticity into spin polarization. Now, in this formula, actually, the energy of the hyperon would play a role. You can see from here. So if you look at the average energy of the hyperon produced in the collision from our simulation, we clearly see that when you go down in beam energy, you will see that decrease. And that's understandable as well, because at no energy, the radial push become much less, and the temperature of the whole fireball, average temperature become less. So your average energy of the hyperon should decrease. So both factors would tell you that you would expect this to turn back down. Okay. So that's what we expected. And then came the star data. I think that was maybe August or somewhere last year. That was really surprising to me at the beginning. You can see this point in particular is the star data from 3 GeV. So this is 10 GeV, this 3 GeV from fixed target. This is basically our curve, which started to turn back down. Okay, that's a huge difference, about factors 2 to 3. Okay, so that was really surprisingly large signal. Namely, even at 3 GeV collision, you have a huge polarization signal, about 5%. Okay. If you look at the angular momentum, I showed you a formula earlier, but that was really applicable only to high energy, because at low energy, like the 3 GeV, your proton is not that relativistic, because 3 GeV beam energy means 1.5 GeV for each proton, and proton has a mass that's almost a GeV. So that means if you have to correct your momentum calculation by taking into account the finite mass of the proton, and that's the angular momentum. Of course, it's obvious that when your beam energy go down to the real threshold, like 2 times the proton mass, this will be 0, because the proton will stop. It's basically come to a stop. Okay, so at 3 GeV, you can see the velocity is kind of getting small. Your total angular momentum is getting small. Eventually, you definitely would see the signal to come back down. But the surprise is that even at 3 GeV, the signal is very, very strong. Very surprising. We look at other simulation that people did. For example, this is a very nice study from Shiguang, Yugang, and Shong and the student with the URQMD simulation. They also see it turning back down the vorticity. We actually compared that the URQMD MPT results for vorticity are quite similar. So it's really that is this kind of mismatch is not due to the vorticity itself. There's also some other study that is called the so-called three fluid model. In this kind of model, you basically treat the fireball, the forward and backward spectator of 3 different fluids that are interacting with each other. In particular, they introduce some friction between these 3 different fluids, meaning that your spectator will be slowed down by your mid-central repetitive fireball. And in that process, perhaps some of the angular momentum of the spectator are transported to the mid-repetitive fireball during the evolution for quite some time. So this is perhaps why in this particular model you could produce a really high polarization signal. But the trouble is that I think many of the model details are quite different from the standard kind of bulk evolution model. And I think that needs to be understood, before one can say that this model is really correct. And also remember, we're talking about a 3 GeV collision. Whether fluid dynamics is good or not is a big question mark as well. So in any case, I think it's interesting and intriguing, the new results. And that would become even more surprising when we add the HADAS data. The HADAS, of course, is a really low energy collision experiment. You can see they added 2 points at the Kyrati 2021. That's in November of last year. This is the gold at 2.4 GeV, I think. This is the silver at a slightly higher energy. Again, you think about it, 2.4 GeV on the denominator and 2 GeV on the numerator. Your angular momentum is really, really getting limited, okay? Yet you get a really strong polarization signal. To me, this is really quite surprising, okay? So then that's a good thing. I mean, at the beginning, I kind of was a little bit upset because, apparently MPT is not going to be able to explain this. But, after a while, I realized that this actually is good, because that means we really have something to understand here in this region. For example, recently, I think the Fudan group had another very nice paper trying to understand this signal by exploring different ways of connecting vorticity and the polarization signal itself. Okay, in this paper. In any case, I think that posed some really interesting new question. When your angular momentum is really getting very limited, how that can be so efficient turn into polarization of individual particles? That may mean something really new. Okay, as I said, what can go wrong? You can look at this formula and ask which part can be wrong. Okay, there are several possibilities. For example, you can imagine a complete failure of this scenario that I introduced earlier, namely angular momentum into vorticity and vorticity into polarization. This could be the case if your whole fireball at 3 GeV is drastically different from 10 GeV. Okay, There could also be substantial out of equilibrium correction, but here the issue is that why that out of equilibrium correction actually keep pushing this signal to be higher and higher. That's not an easy question. Okay, it could be that somehow modeling like AMPT are becoming inaccurate at low energy, but I don't think that's the real trouble, because as I said, we compared. I mean, like a transport, hydronic transport like your QMB produce more or less similar vorticity like the AMPT. I think the most likely cause for now is that the particle production mechanism become real different. Namely, whether you're producing the hyperon via hadronic process or via partonic process. In the MPT calculation, all our hyperons are produced from the parton coalescence, okay? And we use the vorticity value at the space-time point of that production of the hyperon in this formula. So that really, means that when we produce our hyperon from our fiber, we actually are picking up very small vorticity, okay? So this may be wrong, okay? I think that's both good and bad. It's bad that it tells you that MPT doesn't work at 3 GeV, which is not that surprising at all. On the other hand, it tells us that there is a clear shift of dominance in the hyperon production from partonic coalescence to direct hadronic reaction. So I think whatever description that can successfully explain those signals should be able to reflect that. Namely, your hyperons are produced through a hadronic reaction process. And then the question is that how the vorticity or global angular moment can be playing a role in that production process. So this really interesting question. The other question that I mentioned at no energy is that difference between hyperon and anti-hyperon. One of the possible ways to explain that difference between particle and antiparticle is to say that there may be a magnetic field. Remember, magnetic polarization was known when we first founded quantum mechanics at the beginning of 20th century. Magnetic polarization, like a Zeeman effect, was important for people to figure out what's happening in the atomic spectrum. Okay, so indeed, if you have a magnetic field, that will distinguish particle from antiparticle. That is the star kind of extraction to tell us that how much magnetic field you would need if you want to explain that difference between particle and antiparticle or the magnetic field effect. Okay, so you can see that effect become really, really important if you go down in beam energy. But this is just one possibility. But we did try to explore that possibility. This is something like a subatomic version of the Barnett effect. If you remember, at the beginning I mentioned the Barnett effect. Indeed, if I have no energy, your system is rotating and with a large vorticity, and your system is charged. Remember, our fireball had positive inactive charge, especially at no energy due to the stopping of the initial nucleus. You would have quite some inactive charge. And then, the system rotating with inactive charge, that will produce magnetic field. And that magnetic field could cause the particle polarization. Okay, you can add to the formula here, the thermal vorticity formula, an additional contribution due to electromagnetic field. Okay, if you do that and you ask how much magnetic field I would need in order to explain that particle-antiparticle polarization difference seen in the star data, and that's what you need. You need a magnetic field lifetime that is roughly 4 to 5 times longer than the vacuum magnetic field. So in other words, you would need some vacuum, some medium contribution to the magnetic field that would make the magnetic field live longer, because most of our particles are produced at a relatively late time at the freeze out. So you would need a longer magnetic field lifetime. I don't think this is a complete solution to this puzzle yet, but it's a viable and possible solution. The main trouble here is that we need to be able to quantitatively describe a magnetic field evolution that provides enough of magnetic polarization. So that's something we're still working on. So with that, I'm moving on to the next topic. You can see that so far we still have many unsolved puzzles. I only mentioned 2, but there are a few others that I already mentioned earlier. So that point to a general question. How we understand the angular momentum of transport in a multi-particle or many-body system. One of the possibilities to use transport description, like many people are working on Wigner function formalism with finite mass, and when you go to the quantum, H-bar order, you will have spin component of your Wigner function. You can try to use that the theoretical tool to figure out what happened to the spin transport or angular moment transport. Another possible framework from a theoretical perspective is to study hydrodynamics with angular momentum. Okay, hydrodynamics is really about conserved quantities. There are several chapters in our book which touch on those topics. So again, if you're interested to find out more, you should consult some of those chapters. So hydrodynamics with angular momentum, it may help us to understand some of the phenomenological issues. For example, hydrodynamics comes with the ideal hydro, viscous hydro. Some of the non-equilibrium effects would show up with the viscous hydrodynamic term. But in general, this is an interesting question on a theoretical ground. Namely, how do we include angular momentum and spin degrees of freedom into a hydrodynamic framework? Many people have been working on this. For example, the Fudan group, our friend Kenji, and many other people that I list here. Okay, this is perhaps an incomplete list of various groups who have been working on this, and that have been often called spin hydrodynamics. Okay, which I kind of feel that maybe not totally suitable. That I will tell you in a moment. So what do we want to do? That's essentially what goes into this paper with the Fu and our students Anping and Duanshe. So we want to build a relativistic viscous hydrodynamic with angular momentum. Again, let me make this claim that we're not the only one to think about it. Many people have been working on this. Okay, but we have some difference here. That's what I want to emphasize today. So what is hydrodynamics? Well, hydrodynamics is really the idea. General idea is simple. You say that I cannot describe a many-body system really because there are so many particles. I cannot trace each of them. So instead, I do some cross-graining, meaning that I take a hydrodynamic scale, which I call length scale L. That's something we call a fluid cell. We say within this fluid cell, there are still many particles. So they can actually reach some sort of local thermal equilibrium. And that makes sense because for the particle here and the particle there to reach equilibrium, that may take a much longer time. Okay, but for particles within a small domain to reach mutual equilibrium, that may take less time. Okay, so on that scale, I say there's some local equilibrium that's achieved or more or less achieved. So this is my fluid cell, but this is still small compared with my overall macroscopic system. If that is the case, I can then describe a hydrodynamic framework based on fields. Okay, in this description, each fluid cell is like a point, and I have some, I don't see all the microscopic particles in there. All I see would be just the energy and momentum of that cell, and now we add angular momentum. Okay, that's the change. Hydrodynamics deals with only conserved quantities, because whatever that is not a conserved quantity will quickly be dissipated away. So only the conserved quantity like energy and momentum or particle number or charge density, that will become our hydrodynamic quantity. Okay, because they cannot disappear. They can only be transported from one place to another. The traditional hydrodynamics, it deals with basically energy, momentum, and charge density. Okay, and then you use the so-called entropy principle. Okay, in the case of ideal hydrodynamics, you will say the entropy is not generated, so your entropy current divergence will be zero. The microscopic phase, meaning how those particles interact and what kind of particle you have, those only go into the hydrodynamics through the so-called equation of state. Okay, so this is some general idea of hydrodynamics. So the difference now is that we're trying to add angular momentum in addition to all these traditional hydrodynamic quantities. Okay, that's what I want to do. So this is just to explain that, again, so this is just some general idea. If you want to go from the ideal hydrodynamics, in the case of ideal hydrodynamics, you assume the local fluid cell is in complete local equilibrium. In the case of viscous hydrodynamics, you say that this little fluid cell is not completely in equilibrium. It does feel the surrounding. Okay, so there will be gradient terms that go into your energy momentum tensor, your charge current, and your entropy current. However, the evolution should be such that your entropy only grows and not decrease. This is the requirement by the second law of thermodynamics. If you require that, you can actually determine how those viscous term will look like a transport current, like the bulk viscous term, shear viscous term, or your heat current, they have to take specific form to ensure that your entropy only grows. So this is a very well-known story, and that's not very stuck with viscous hydrodynamics. Okay, so what we want to do is that we want to do exactly the same thing with angular momentum. Now we're adding angular momentum conservation because angular momentum indeed it also conserves the quantity. So what goes into angular momentum? You have to write down the angular momentum in terms of hydrodynamic field. Okay, that's what you want to do. You obviously have this, typical orbital contribution. That means, so what is this? This is essentially the X cross P or R cross P. That is the angular momentum or orbital angular momentum of your fluid cell with respect to your global frame. Okay, this is the trivial part of your angular momentum carried by this fluid cell. In addition to that, you have a sigma, angular momentum tensor. This is reflecting the internal angular momentum. It's like the internal energy density or internal charge density of your fluid cell. This is the internal angular momentum carried by your fluid cell. Okay, so basically we introduced this sigma mu alpha beta, their local angular momentum current. There's the local angular momentum density sigma alpha beta as a function of space-time, and corresponding there the angular momentum chemical potential. Let me say that in many other studies, these are simply called spin current or spin density or spin chemical potential. And there is a reason why we wanted to call it differently. If you think about it, conceptually, it may not be feasible to separate the spin part out of the local angular momentum. Okay, we're talking about a coarse-grained fluid cell. To illustrate my point, think about this very simple example. You have 3 particles forming a cluster. Okay. Of course, this is eventually like our fluid cell, but using 3 particles make it very simple to illustrate. You count how much angular momentum this cluster carry with respect to your global fluid, global frame, where you write down your hydrodynamics. Well, there's always X cross P. X is the position of your center of mass of this 3 particles. P is the center of mass momentum of this cluster. And then in addition, you'll have this contribution. The X prime is the relative position of 1, 2, or 3 with respect to the center of mass of the cluster, and the P prime is the relative momentum of those particles again with respect to center of mass. So this is really the angular momentum with respect to the center of mass, and there could be internal angular momentum like spin, or it doesn't have to be spin. If you think about even classical fluid, let's say of some large molecule, chiral molecule, or some molecule with vibrational rotational mode, they can carry internal angular momentum. That's not associated with the mechanical motion of the particle. So all these actually go into what I would call the sigma, and that's the internal angular momentum. It's really a conceptual question whether you can say the spins of those particles can become an independent hydrodynamic variable or not. That's a question mark, I think. Okay, so once you set up your system and then the rest is kind of automatic, you just pretty much do what the Navier and Sachs did. You say, you start with ideal hydro, you assume everything's locally defined in this case, and your angular momentum current is just angular momentum density multiplying your local rest frame velocity, and then everything just goes automatically. This is a kind of more or less trivial. What we want to do is that go beyond that to build a viscous hydro with angular momentum, and that's much less trivial because it's getting a lot more complicated. So basically, all your hydrodynamic quantity will have a viscous term that should have the gradient term up to the linear order in hydrodynamic quantity. And what's important that you want to figure out what happened to the entropy density. Especially your divergence of the entropy current should be positive definite. Okay, so that's the key requirement. At the leading order, you do this calculation of partial mu S mu to the linear order of gradients. You would see some term like this. So we interpret this as the requirement that your anti-symmetrical part of your angular momentum, your energy momentum tensor should be 0. Okay, at viscous order, and then next order contribution to partial mu S mu goes something like this. So by requiring this to be positive definite, you can basically write down all your viscous correction. Like for the T mu nu, you would have the bulk pressure, the bulk viscous term, and you would have the shear viscous term here. So this is in the so-called I-card frame, where your charge current has no viscous correction in this water, and then your angular momentum current will have several viscous correction. Okay, and these are just written down in terms of general Lorentz structure decomposition. And if you work out all the details, that's what you get. Okay, it's quite complicated, which is understandable because there are now 3 indices to deal with, and you also have the complication of those T mu nu and M mu. In any case, we find that there are 5 different contributions into this sigma mu nu, sigma mu alpha beta in the viscous water, and that means we also have some 5 transport coefficients. These are just like the angular momentum transport mode. Okay, the coefficient for angular momentum diffusive mode. Okay, so I don't want to go into technical details, just want to say that that's essentially what we did in that paper. And you can do the same thing in the so-called Landau frame, where the T mu nu becomes simpler, but the charge current becomes more complicated. You basically get the same result. Okay, so I think that's what I want to say. I think the most important message I want to say that I think there are still many interesting questions to be understood, like the conceptual issue, whether you can really treat the spin current the independent part, where you really have to deal with the angular momentum, which include both spin and the internal motion within the fluid cell. Okay, so these are questions that need to be understood further, and how to understand the difference between different works that I mentioned. So that's, I think, what people are working on now. Hopefully we'll have some progress in the last couple of years. The last topic I want to discuss is the phase structure. I think I have a few more minutes. I think that should be enough, more or less. Phase structure and rotation. This is also an interesting topic. Actually, in this book, we had a nice chapter mainly by Xu Guang and his student Holly together. Essentially, they said, in addition to temperature and baryon density, you can add a control of rotation, and you ask what happened to the material structure, like chiral symmetry, like what happened to color superconductivity, what happened to chiral symmetry restoration, and so on. Indeed, that's an interesting question. Rotation mainly affects the spin degree of freedom or angular momentum degree of freedom. Okay, if you have a system that has fermion pairing in the scalar channel, well, that's actually relevant to us because there are many examples like superconductivity, Cooper pair, superfluidity, chiral condensate, diquark in color superconductivity. They all have 2 fermions pairing in overall angular momentum 0 state. And that actually become kind of unfavorable when you have rotation, because rotation tends to polarize all angular momentum, both N and S, and that would actually typically suppress the scalar pairing channel. So in this picture, I'm schematically showing a situation where your 2 fermions have spin in the parallel case, where the orbital part in the p wave going in the opposite to the spin, so that your total angular momentum is 0. Okay, this is relevant to the chiral condensate. Or you can have 2 fermions in the S wave channel, in the orbital S wave, meaning there are no orbital angular momentum, but their spins are anti-parallel in the singlet configuration. So in this case, total angular momentum is also 0. Both of these will become unfavorable because when you have strong rotation, that would force all these angular momentum spin orbital to be aligned with the global angular momentum. So that will suppress those kind of pairing mechanism. Indeed, that's what we found by doing a calculation, the Nathaniel model. So for example, for the QCD chiral condensate, if you start turn on rotation, you can see the chiral condensate will start to decrease when you increase the rotation. Okay, so that has been clearly seen. You can actually even think about, and depending on the temperature, this could be a smooth crossover or a first order jump, okay, when you increase the rotation angular vorticity. So that means you essentially have something like a phase diagram on the T omega plane. So at no temperature and no rotation, you would have the usual chiral condensate. But when you increase temperature or increase rotation, you can go through inner crossover or real phase transition to a situation where the chiral condensate, chiral symmetry is restored. Okay, so rotation can actually help restore chiral symmetry. That's the message. You can also study the high density quark matter where the color superconductivity is present with the Cooper pair pairing between diquark. And we found that this pairing gap also become less and less when you increase the rotation. Okay, and depending on temperature, and the high temperature, again, this is the crossover, and where no temperature is the first order jump for that color superconducting gas. So this is the general phenomenon. Basically, your rotation suppresses kind of scalar pairing. But then more recently, we got interested in another interesting direction, namely what happened when you have not only just the rotation, but also isospin. There's a reason for that. The reason why we consider it, well, if you think about the no energy heavy ion collision, or think about neutron stars, not only that you have a very high baryon density, you also have a finite isospin density, because your number of neutron protons are not equal. Actually, there's a big difference between number of neutron and proton, both in heavy ion collision and in the neutron star environment. So you would have a finite isospin density. And as I showed you earlier, in that kind of no energy collision where you're here, there's strong rotation as well. So you have both strong rotation and isospin density. The question is, what happened to the matter, structure? And that's our recent paper a couple of years ago, which was published in CBC, the cover story. So this is what we found, basically. The vacuum morphism is dominated by the sigma or chiral condensate. If you have a static matter with finite isospin or high isospin, that will become a pion superfluidity, as many people pointed out. Many groups actually studied it, for example, the group in Tsinghua and CCNU and so on. But if you do have isospin density as well as rotation, you would actually be able to see an emergence of a rho condensate. And again, physically, that's very intuitive, right? Your rho has both carried a finite isospin charge and also spin one, at angular momentum. And that will become very favorable if you have large isospin and a large rotation. That's what we showed again with our model calculation in this paper. You can see this is the condensate of the function of isospin density under non-zero rotation with 80 MeV of rotation. You can see the pi basically is suppressed. There are no more pion superfluidity. Your sigma chiral condensate is suppressed by the isospin, and your rho condensate start to emerge and become dominant. And the same can be seen in this plot where we plot the condensate of rho as a function of omega at a different isospin density. You can see at high isospin density is very large and keep growing with the rotation. Okay. And that also leads us to this kind of interesting phase diagram on a new parameter plane, namely on the rotation and isospin plane. You can see that at zero baryon chemical potential or quark chemical potential, you have a phase diagram like this. You would require somewhat large vorticity to see a rho condensate. However, when you have a large baryon chemical potential or quark chemical potential, that really helps the emergence of a rho condensate. You only need something like omega on the order of 50 MeV and isospin density on a few hundred MeV to see this rho condensation. So I think there are really like rich phase structure of isospin matter and rotation. They can be relevant to low energy heavy ion collision or neutron star matter. They could have implementation for particle polarization, dilepton production, chiral distortion, and so on. Okay, so these are things that we're going to continue to study. So that brings me to my summary. I hope that in the past hour or so, I was able to convey some interest in developing our field along a new direction. Namely, there's a new regime of study for strong interaction matter. That's when the matter has a large angular momentum as an external control. I hope I showed you that the non-trivial fluid vorticity structure will emerge, which will induce the global and local polarization phenomena, especially in the no energy heavy ion collision. I discussed some of the development of hydrodynamic theoretical framework to incorporate angular momentum as a new degree of freedom. I also discussed some of the new and rich phase structures that are brought by the rotation. Okay, there are many more interesting questions before explored. Let me say that I particularly want to emphasize that there's an exciting new regime at low energy, namely highly polarized strong interaction matter. If you look at this beam-energy dependence of the hyperon polarization or other hyperon like omega or cascade, and also the rapidity distribution, they all suggest that when you go down from 100 GeV to 1 GeV collision, there surely is a disappearance of the partonic collectivity. like a nearly perfect QGP fluid, there is the appearance of spin collectivity in a high polarization strong interaction fluid. So that's something that would be really interesting to see. Okay, the reason I say that is because the fireball orbital angular momentum is really a global quantity. The orbital angular momentum is because the whole system. Okay, that's where the orbital angular momentum comes from. So the polarization, if there's a really efficient polarization, that means there is some strong spin collectivity and efficient angular momentum transport in that regime. So that'd be interesting to figure out. Let me say that on a bigger background, there are lots of interesting current and future experiments for relativistic nuclear collision on the order of order 1 GeV collision. There is the star fixed target that was completed. There's HADAS that's going on. There is the future HAF and FAIR and possibly NICA. They're all in this energy regime on the order of 1 GeV, one or a few GeV. So I think it's really a potentially new, interesting, integral component of physics in that energy regime. That brings me also to a discussion of what I said so far in the first 2 seminars. I think I've been focusing on really the spin degrees of freedom, and it's particularly the interplay of microscopic spin with the macroscopic chirality, vorticity, and magnetic field. In the first seminar, I talked about the chiromagnetic effect, which is essentially the spin polarization by chirality and magnetic field together. So in this talk, I discussed the spin polarization by rotation. So these are all novel phenomena in the strong interaction matter due to the spin degree of freedom. And I think there are many more interesting things that will come. So stay tuned. Thank you.